We should start now.
Oh, okay. Good morning, everybody. On behalf of KDK College of Engineering, I, Dr. Sangeeta Wankhede, convener of this STTP, welcome Dr.S.K. Omanwar sir, former head of the Department of Physics and presently working as UGC BSR faculty fellow at Santa Gadge Baba Amravati University, Amravati. Actually, sir is guiding me since very long. That is from 1984. I also welcome all delegates and my dear participants. Today is the 4th day of STTP and the topic of this session is Luminescent Materials Processing and Applications. I will request participants to drop your queries at the end of this session. Now I request Tulankar madam to throw light on brief CV of Omanwar sir. Madam, please.
Thank you so much, Wankhede madam. A very good morning to everyone. Today on this 4th day of STTP, I am very glad to introduce another eminent speaker in this series of talks, Dr.S.K. Omanwar, Senior Professor and former Head of Physics Department and presently the Distinguished UGC BSR Faculty Fellow at Sant Gadge Baba Amravati University, Amravati. He has had a meritorious career throughout, and it is a great achievement that he completed his education till postdoctoral research with scholarships right from 5th standard. His thesis was awarded the Best Thesis Award of BRNS DAE in 1985. He has a vast teaching, research, and administrative experience at postgraduate level. His research career is distinctive in developing inorganic luminescent materials for various applications like mercury-free lamps, display devices, LED-based phototherapy devices, solar PV panels, CFL bulbs, PL LCD, and PDP panels, etc. He has completed several projects and published above 560 articles and research papers in reputed journals indexed in Scopus. He has guided 25 students for PhD. He also has patents to his credit. He has received 26 awards and 178 recognitions, which include the Lifetime Award by Luminescent Society of India in February 2020, that is very recently, Fellow of Maharashtra Academy of Sciences in 2015, Dr. B.T. Deshmukh National Research Award in 2016, Outstanding Scientist Award in 2018 by Innovative Industries Association, Chennai, UGC BSR Faculty Fellow Award by UGC New Delhi in 2019. Recently, he had participated in the IUMRS ICA 2012 at Busan, South Korea, and is working as a member of 11 international advisory committees. So let us all welcome such a man of knowledge and repute and hope his talk today will be greatly valuable for all participants. His topic for today is luminescent materials, processing and applications. Over to you, Dr. Omanwar, sir.
Thank you so much, madam. Very nice introduction. And since first day itself, I am looking for excellent comparing by you, madam. Thank you very much for having such a gesture.
Thank you, sir. Thank you so much.
So, shall I share my screen now?
Yes, sir. You can.
Yes.
Okay. Is it okay? Hello.
Yes, sir. It is clearly. It can be clearly.
And am I audible to all?
Yes, sir. You are audible too.
Audio, video, both are clear.
Okay. So at the outset, I am very much thankful to convener since beginning, Dr. Yogesh More, who was so some time, convener of the event, principals of the both institutions and management members, and complete organizing committee for inviting me for this course. I dedicate this particular talk to my guru, late Professor Dr. B.T. Deshmukh sir, who was head of the department of physics, Nagpur University, and also Dean Faculty of Science. Actually, he has nourished all we people very nicely so that we can do something better than our own expectations. A tribute to Dr. B.T. Deshmukh sir. Actually, I was the director of Swami Vivekananda Kendra for about quite more than 6 to 7 years in our university. And we think that, we wish and we hope that Swami Vivekananda is the torch bearer of all of us. I quote only one example regarding attitude. Max Muller, who has invented eraser, he said, it is for those who make mistakes so that they can easily erase the things. However, Swami Vivekananda said, erasers are made for those who are willing to correct their mistake. So this kind of attitude, we Indian researchers, we are having, that we know our limitations, we know that what exactly we used to do. He said that look at this science. It has discovered a lot of things. It has made life absolutely different, but it has added to our tensions and worries. The present situation, you will see that how much tension every people in the world is having and how much they are worried about this COVID-19. This is only because our emotional orientation is not right. Whatever science which has invented, these are to be used for peaceful life. But we people, because of learning in science, because of our emotional orientation is not right, we are facing these tensions and worries. Recall from last two presentations, Dr. S.V. Moril sir has illustrated very nicely that learning science, we are able to give innovative ideas and concepts. Lot of ideas and concepts we learned from Dr. Moril sir. He is really a torch bearer for we people. Many ideas he has just discussed, then we implemented. All researchers, we were students of Dr. Moril also. It has made researchers to implement and verify whatever concepts and ideas that are being proposed. Accordingly, the technology has to be invented for better and peaceful life. And second lecture, Dr. Gupta sir from Hyderabad, he is a very means cooperative to Luminescent Society of India, and what he has assured in his lecture that India has initiated the fabrication that all UV semiconductors he was talking about, Atmanirbhar, and very soon the import substitution will be established. The UV will be made available at very low cost. That is, he has assured. My proposition is a different thing. My processing of luminescent materials. Whatever luminescent materials are being invented and their applications, we should see that. We should see that how it has to be processed for real applications. It is just like whatever beauty parlor people used to do on the process, the materials which are being invented. The focus would be cost-effective methods for the materials. A single material can be prepared by various methods, but which method can provide you the better product? That means precise performance. People are going for getting the high intensity, but high intensity without precise performance is not useful. We can compromise on intensity, sensitivity and intensity, luminescent intensity, but precise performance is more important. And third, using resources optimally. Whatever resources which we are having, these are to be used optimally and looking at the sustainable development. Dr. Boril sir has explained the luminescent material, role of luminescent materials for increasing the photovoltaic conversion efficiency of the existing solar cells. Most of these solar panels are being established, erected all over the country, not only the country, all over the world. There are big countries, rich countries, they can replace their photovoltaic panels by new semiconducting materials having high photovoltaic conversion efficiencies. But the country like us, most of the countries in the world belong to our category, developing countries. They are not ready to, they are not, cannot afford to replace the existing solar photovoltaic panels. The Dr. Boril sir has given the concept and innovative idea, and on which many people, we are also working on that, two persons to get PhD out of it. The material which is to be means disseminated, dissipated, that material is to be mixed with the adhesive like Teflon. Just like the car's life is being enhanced by coating it with Teflon. If we disseminate this nanophase material in Teflon-like structure and just coat such things on the solar panels, we can have higher efficiencies for photovoltaic conversion, so that whatever existing panels are there, those can be used effectively. And that is what we are looking for, the sustainable development without much investment. So the topic is luminescent materials processing and application. I will give a few examples for this processing. Before going to that, fundamentals, those who are not belonging to this luminescence field, I will just enlist the definition of luminescence. Luminescence is defined as the emission of light by bodies which is in excess of that attributable to blackbody radiation and persists considerably longer than the periods of optical radiations after the excitation stops. The materials exhibiting this property are called as phosphors or luminescent materials. The principle is that whatever radiation energy is there, the excitation process goes to activator, that is spontaneous emission, and second one, B1, is first it is sensitized, then transferred to activator, and then emission occurs. The mechanism with reference to your configuration coordinate diagram illustrating luminescence process, that the ground level and excited level, there are splitting of those levels, and you can have excitation by absorption of energy, and then non-radioactive transition, and then emission of us. The luminescent materials have got different applications, and those applications are radioluminescence, photoluminescence, cathodoluminescence, electroluminescence, and various spontaneous stored luminescent solar concentrator, thermography, then your thermoluminescence, and all these other luminescence and their devices where these are being used. TLDs, that is thermoluminescence dosimeters. Now the new term has come as OSLD, optical materials. The depending on excitation energy, the phenomena is being prefixed that radioluminescence means radio frequency, photoluminescence means photons, which exhibit luminescence. Then thermoluminescence means thermally stimulated luminescence. The materials comprising of the host materials, all blue, that is second block, to some extent third block elements, and then you can go from 12 to 17. 18 is all that blue boxes combines metals and alkali and here negative ions, the host material, then dopants, defects and impurities. They are real means sensing or making the phenomena happen. And then dopants like activators and sensitizers. You can have rare earth material, transition metals, and the 5, that is 50, 51, 81, 52, 83. These are the things which can have -2 plus, and those are the defects and activators which can be, these can be used as activators. If you look at to the lighting applications, you will see that there are many applications, lamps, filament lamp, which are invented in 1878, 1882, then solid state lighting and gas discharge. And we are very happy to specifically mention here that we have made first for solid state lighting, then CFL also, and mercury-free lamps. These are the VUV lighting devices. We have also used VUV excitations from the Chinese Academy of Sciences collaboration, and we have exhibited the performance of our own phosphorus and revised the phosphorus. Actually, we do not have that particular facility here, but we could get those things. And this is the light emitting diodes present status. What you can get is all LEDs and white LEDs, WLEDs. The materials which are being prepared by different methods are to be characterized. First is the X-ray diffraction technique that everybody knows, mini-flex tool, which we are having the tension same model. This is again obtained from Jalgaon. Then we have got the Hitachi 700, F760 optical luminescence, and the furnaces the same, FEACM, ELOSL. This is what the facility which we could get from the Beijing radiation facility, BSRF facilities, and the BSRF facilities in air view is being given, and this yellow VUV 4V8 line is being used by us remotely, and this is the actual facility which is being put there. Earlier, 2010 to 11, we obtained from AC funding, and second effort which was taken by Dr.S.K, who is also our student, and collaborative program in but nowadays we get directly the facility from micro. The red line indicates that collaboration is there only with in our country. Our group is using that one, and rest of the other country. This is a collaboration later since October 2013. We are collaborating, and more than 300 samples we have actually examined and reported. 2 cases have come out of this particular collaboration. The protocol and other things are there. I will not go into details of this facility. But anyone who is interested in getting this facility, we will be very happy to provide the link so that we can introduce those people and they can get directly remote access. You can record, you send the sample, you can record all those readings at your desktop. So processing of the materials for desired application and performance testing, these are the things which are important for today's sector. I will take few examples here, processing parameters for. First example I'm taking is yttrium based luminescent materials development, yttrium based. And if you go for yttrium, why yttrium? That is the first question. That if you look at the applications of Y2O3 doped with EU, that is European, that is being used in all the display devices, in all the lighting devices, with the purpose of which is just to give you a red light. Yeah. The reasons for its development. So we did some processing which is related to purity of starting material, because Y2O3 used to come in 3 different purities: 99.0, 99.9, and 99.9. We did experiment on all the 3, and we have presented these results and published also. Then modification of excitation was the second aspect which we have taken. And then cost evaluation being done, and few examples on yttrium based phosphors are Y2O3, YPO4, YBO3, and YBO4. I will take one example out of this and then we shall proceed. Why yttrium? The facts. The narrow band lamp phosphors. It is being used in tricolor lamps. It is being used in plasma display panels. The size requirement is 2.5 micrometer. Then up conversion with YOF, ERYB, IR to visible conversion 2%. Then CR tube reference applications and all, along with FE brightness 100% color TV, then field emission displays, solid state lighting. Most of the red emitting parts are based on yttrium cost. The cost of the device will be high because of yttrium. Yttrium is cost. At commercial level, people are using conventional solid state method. And this method, we find that this method is not useful for getting optimum performance, that is precise performance of the plasma. The RGB combinations are produced, the white lights. And Y2O3U is the red, which the share is 60% by weight. Then CMGL11 on 19 kb phosphor, that is 30% green, and BAM is 10% blue. So for LED, the weight percentage of red is also more than green and blue. So the Y2O3's share is highest. So in 2004, what we have presented, we attempted developing novel methods of synthesis of phytonutrients with a special reference to what? Cost reduction and improvement in the luminescent water. See, the improved performance at lower cost, that was the object for this whiteboard. What we did, we have tried our level best to find out the replacement of Y by LA. And we have prepared all these samples by co-precipitation, not solid state synthesis, solid state diffusion, co-precipitation of yttrium nitrate, lanthanum nitrate, and iridium nitrate using oxalic acid. Then forming European dope mix oxalate of yttrium and lanthanum, and which on subsequent decomposition forms YLA2O U3 plus phosphate. Other methods are also attempted simultaneously. This is what the flow chart. The same thing, boiling in concentrated geometry. The ingredients are added. The aqueous solution of these nitrates was prepared by reduced water and precipitated by solution required from oxalic acid. We added the precipitate of European dope in yttrium. Oxalate is formed, was dried, and then oxalate was decomposed in the disintegrate formed in the body and fine powder of the. The resultant oxide was calcium at 1000 degrees centigrade, and then suddenly quenched to room temperature. So you will see here three different emissions. Series A, Series B, Series C. Series C is your 99.99% purity. B is 99.9 and A is 99.2. Secondly, when La is added with a different concentration, you see the graph. The excitation spectra is getting shifted from this to this pink. And pink is the maximum. So excitation, why this excitation shifting is to be expected? Because its excitation spectra for pure 2, 3, you will see that the excitation maxima was 246 nanometer. And the intensity in arbitrary units, which was counted on that machine, is about 612. By addition of La, we have shifted with 0.17, shifted from 46 to 47. Like this, contribution of La is being increased, and serial number 5, you will see that the excitation spectrum, which is the pink at 253.7 nanometer, and the intensity was maximum. Further addition of La has decreased the intensity and excitation gets shifted. But this is only because that for 254 is the mercury discharge, that is excitation line, and 254 nanometer where the discharge variations are maximum, and therefore the material should such that material should absorb maximum, and that is what is getting reflected in the emission intensity. So it is the improvement in the performance of the material by addition of La and thereby shifting the excitation spectrum. If you evaluate the cost reduction plot, we have evaluated the cost of the comparison with your Y203 and the this is performance. So the performance which is maximum, which will be for incorporation of La. The cost evaluation being done A, B, C. That is, C is 99.9%. That is, the costs were at that time 2004, and 99% cost was 3,260. And incorporation of LA, it has reduced to still lower cost. And if you combine these two, that is 99% and the incorporation of LA, we get the Y2O3 YLA system improved performance at lower cost. So this is we think that this is what is called a processing. Second parameter, the things are that the student, Dr. Now he is awarded his degree, Dr. Kishore Kopar. He has been given to improve upon ATM based process. And what he did, he has selected Y2O3, YBO3, YPO4, U3 plus, and YBO4. And in all these hosts, he has prepared these materials by different synthesis method, and then performance is being verified. The criteria was very much simple. We wanted to have a best suitable method for best performance of the phosphate. And that is what is being done. That the U3 plus usually locate two symmetry sites in atrium based phosphorus. One is non-centrosymmetric site, that is 75%, and therefore we used to get a 611, 630. And when it is located centrosymmetric, 25%, then we can go for this responsible J is equal to 1, this is responsible J is equal to 2. That is 5949. The different behavior of U3 plus ion in two different lattice sites is most probably due to the large diameter, that is 0.95 angstrom unit of U3 plus ion, which fills the lattice sites of the host and gets affected by those nearby atoms. And these are energy states 5D2, 5D2, 5D3, 5D2, 5D1, 5D0, and 7J, 0, 1, 3, 4. So the transition levels of U3 plus and corresponding wavelength is being given. And this is the dominant, that is 613, which is the same. So 5D0 to 782 is the main transition, which is the answer. So drawback of presently used red phosphorus. These are presently used in various commercial applications. And these commercial applications, many lighting and display devices Y2O3 or atrium-based phosphorus are used. Y2O3 U3 plus phosphor to be a dominant component by weight and so cost also. Then YBO3 U3 plus is the strongest emission peak is at 595, means centrosymmetric U3 plus, corresponding to orange red color light from 5D0 to 7D, transition of size. Instead of a red one, whereas the concentration of 5D0 to 7D2 emission is preferred in terms of the application. And therefore, YBO3 needs to be improved for getting the dominant transition 5D0 to 7D. Then YBO4 U3 plus is also being used in many applications commercially also, but it has got mismatched spectra for solid state lighting applications. If that spectrum modification is being done, then we can go for solid state lighting using this YBO. So Y2O2, yes, U3 plus, it has poor chemical and photostability mismatch absorption, high cost, and unsatisfactory efficiency. How one can improve that YBO4, Y2O2 yes, performance that is presently which is being given to one of the students, and the results are. So selection of amongst U3 plus activated Y2, YPO3, YPO4, and YPO. To select best method such as low cost and gives optimum luminescent intensity. And controlling over particle size and its distribution by optimization and modifications in the method of the synthesis. So partial replacement of Y with the suitable trivalent elements or getting a low cost and also the shifting the excitation level so as to match the discharge of radiations. So selection of a method. So we have prepared this first course by 4 different methods: solid state diffusion method, which is being commercially applied for most of the application; combustion method, which is being we are using last 13 years. We are using combustion method for inorganic material synthesis; aldo-keto gel method, then co-precipitation, recrystallization, or slow evaporation method, which are wet chemicals. Solid state diffusion method, the flow charts are there. One can get the flow charts and metal oxides and protons mixed thoroughly in the mortar. On right at 50 degrees centigrade, heated at subsequent 400, 600, 800, and 130 hours at each step, which intermittent grinding also, then wait for the in combustion, what usually urea and ammonium nitrate we are using, fuel and oxidizer, metal nitrates, is starting precurses and dopants. Adding distilled water, 20 ml, studying with homogeneous solution, slowly heated at 90 degrees centigrade in order to remove the excess of water, and then kept in resistive furnace preheated at 500 degrees centigrade plus minus 10 degrees centigrade, stirred in air, sintered in air, 800 to 900 degrees for 2 hours, and quench. Then white water. Then next method is the aldo-keto gel method. So nitrate precursors are initiated, and then benzaldehyde and acetone, then stirring slow to 130 degrees centigrade, and then cooling. A red gel is being formed. Then heating at 300 degrees centigrade, dark red foam. Then carrying of resin at 450 degrees centigrade, shining black foam and charcoal, then sintered at 800 to 900 degrees for 2 hours, quench, white powder to be obtained. In co-precipitation and recrystallization, the simplest method, that metal nitrates and solutions of metal nitrate, aqueous solutions of precipitating agent, drop out, filtered, dried, filtered. So selection of trivalent is been done at Bi3 plus and Gd3 plus. They are selected only because they are good transporters. And Al3 plus and La3 plus, these are being selected because low cost and capability to modify the spectra, means excitation. The first example, Y2O3U. We have prepared this material by co-precipitation, aldo-keto, combustion stage, solid state. And lower on black is XRD's ICD file number given, and all the methods use perfect matching with this particular file. And we have seen that if the PL is recorded, we found that PL is the maximum for the Y2O3 to be prepared by co-precipitation. This co-precipitation is the simplest method, and commercially people are adopting solid state diffusion methods for commercial applications. But if one can go for co-precipitation, we assure that its PL potential is wrong. These results are also published in good reputed journals. I will view the list. We have tested these 4 products: A, B, C, and D. A is for SSD, B is combustion method, C is adopito, and D is prepared by co-precipitation. And if you look at the particle size, even from their scanning electron microscope, and here the particle size distribution. How many particles belongs to, means what percentage of particles belongs to what particular size, that is being plotted. And 4 graphs on right hand side, you will see A graph is the SSD particle size. The distribution is broad distribution, and the center peak is also at a larger size. And if you look for this combustion synthesis, you will see that the particle size is getting reduced. But there are also the possibility of getting larger particle sizes. Here the distribution is narrow. Aldo-Keto method gives you very good particle size, and most probably the if you look at the photoluminescence of Aldo-Keto product is also comparable with the co-precipitation. But here the full width at half maximum, if you calculate, the particle size distribution is wide. Whereas co-precipitation method gives a narrow distribution. All the particles, most of the particles are of equivalent size, and that is why we can say that the co-precipitation method gives you optimum here. So this kind of investigations are very much necessary for a given phosphor. You prepare this phosphor by different methods and compare them on the desired parameters. The particle size becomes an important parameter because these phosphors are to be coated, and whenever these phosphors are to be coated, the particle size matters. If you are having this identical particles, the thickness of the layer which is being coated on the actual applications, that is becoming say uniform. So uniform coating is very much necessary, and therefore you should have a very narrow distribution. In some applications you require a nano size, micron size, submicron size, and so on and so forth. Depending PL density, you see the red graph here, excitation and emission. Red is a co-precipitation, blue is the Aldo-Keto method. As we have seen that the Aldo-Keto method product is also having narrow distribution side, and exactly below the co-precipitation. Then combustion, and then means the combustion solid state diffusion method is being used for commercial application, and which is having very low as compared to the product. Only replacement of the method improves the performance of the phosphor. Therefore, we should look for the precise performance so that we can compromise on the sensitivity as well, but precise performance is very much necessary. This is again a processing of the luminescent materials. If you process them properly, and if you reach to desired particle size, then we hope that the product so this is what the intensity and estimate. And we try to understand as say LA is replaced. Y is replaced by LA. Y is replaced by LB, GD, and DL. If you go for a simple cubic structure, what you do, and once you try to replace this LA, the cubic structure is getting changed to hexagon, and that is what the stretching, and this stretching might change the hexagon. Here cubic is getting changed to diagonal. Here there is no shifting of excitation because both are having and here this also. So the performance by replacing Y by LA, AL, GT, and DPI is also being seen here. You can see here this LA pure, then LA, variation of LA first, and you see that optimum PL is obtained earlier, that is Y203, and then the performance can be improved for that shifting of excitation. See here, 254 nanometer excitation, and emission is monitored at 613, and you will see that the Y203 is a pink. That pink graph is like this pink, and this Y203. And this red, you can look at the red. Red is what? Incorporation of LA, and you will see that the red is emission also. So shifting of excitation by incorporating LA has improved the performance of the Y203. This is what is being practically observed for Y 1.7, LA 0.3, and then U2. The CI color coordinate diagram is also modified by incorporation of LA, and it is going to be red. That will improve shifting towards the right side is preferable, because if it shifts towards upper axis, upper side, then it will go to orange red, and that is what I say. So in this also has been partial replacement with AL. So why AL? You will see that this Y203 is here pink, and last one is the YLA, is green. You will see that the incorporation of AL has not affected the excitation, spectrum modification. The Y203 U is the best. A very small quantity which is being seen is AL 0.8. Here also you will see that L203U is having this particular color coordinate, and this is Y203, and this is 1 AL1 O3. But this performance is not useful for lighting applications, but some display application, this first one is very much useful. For GD also, we did the same, and performance Y from GD for few applications, the intensity maximum for this 630 nanometer opted for 500 nanometer. CI diagram also gets modified, and it is going towards. Then BI replacement is also being done, and you will see that optimal PL is opted for this, and here you will get U3 plus Y plus, and different combinations for red is that is the maximum one, for white means BI is one used to do that publishing is supposed to be first detect an online evidence. The performance of this is being done color coordinates, and for summary one can go for what have is the what you are having DI and G. 5U4, here also we adopted this 4 instead of co-precipitation. Here recrystallization method we use, and here aldo-keto combustion, and you see the performance for this 5U4 you first one. You will see optimum performance for solid state. So SSD technique, but there is a wide range of particle size and distribution. Here, controlling particle size, the methods that can be modified, particularly aldo-keto method can be modified so that we can have a narrow distribution of particle size here. And this, you will see that the most of the particles are of identical. The other part was YLA, the same strategy we adopted for YLA4, and we have tested for the results. I can see here the red one is YLA4 and 6.3. The results are published. The same thing, I will not speak more for these lithium-based compounds. Then other coordinates, YPO4. You will also see YPO4. Recrystallization method as given this phosphate APM YPO4. First one. For this YPO4 you request for recrystallization very narrow distribution of particle and optimum performance. This is also being useful, and this is also being published. This is also being published. It's almost YPO4. So XRD, what we are doing here, we are adopting different methods. We are checking for the XRD, whether the product is being formed. We are checking for luminescence and particle size distribution. So if you have a particle size distribution facility, we do not have that particular particle size testing particle size, and we had a collaboration with people from Mumbai, and we could get those characterization done. XRD can be done elsewhere. Whereas teachers who are working at college level, they can also prepare a strategy to plan this kind of work for a selective phosphorus. Only the synthesis is important, and synthesis is by wet chemical method. You can adopt this synthesis techniques or synthesis facilities that are available at every destination. People can plan a good piece of work by on processing of the material so that optimal performance can be tested for the required parameters. And for desired application, what is being required, what particle size product is required, what is the performance you are expecting, where it is being applied, all those questions are to be first seen, means literature should be collected, and accordingly the strategy is to be. In this YPO3 borate or phosphorus also, you will find that the solid state diffusion, combustion, synthesis, and recrystallization. The recrystallization, the performance of the particle size is smaller, and optimal performance, you will see that for recrystallization with saturation and this is elevation. So see the optimum PLA intensity for recrystallization. This is also published in Sphere journal, and same strategy is being adopted here also. This Dr. Popper was very systematic worker, and I'm very much happy with his work because he has taken a lot of things for doing all those things on few selected phosphors for desired applications. And all results are being published in standard journals. He has got about 12 publications out of his thesis. What he did, he only prepared the phosphorus and then characterization is done by the instrument. Wherever that characterization facility is available, one can go to that destination and do analysis. Only thing is that the proper thinking is very much necessary. Then second example, which is TLD materials, and for TL application luminescent materials development. Here I will take only two examples, and one is CSO4, and here Dr. Wilson has helped us with suggested many things for implementing CSO4, and Dr. Nitin Ingle has taken all efforts to prepare this as a CSO4 UI, U, UP plus and UP plus phosphorus to be prepared by different 14 different strategies being adopted for improvement in CSO4. And this paper is published your very standard nuclear hazards. So 14 types of modifications and very good paper. It is having many citations. Actually, the phosphor which is being used here, so-called phosphor is being used widely in our country. Importing this particular phosphor from Horsham is very difficult because the cost of LFTLD100 and other phosphors, standard phosphors for TL purposes, this is costly, and therefore we are using CSO4. But we suggested very simple techniques for preparation of CSO4 UI and yet improve performance as compared to the Tech 288 of CSO4 UI and also what is actually the requirement for a TLD? Nowadays, people are going for optical stimulated developing so many. Before yesterday, high dose dosimetry patent to Dr.S.K from KDK, the host institute. I take this opportunity to congratulate her, and all participants are requested to just clap for her for getting the patent day before yesterday, that is 18th of June. I'm very much happy and proud of Sangeeta Wankhede, madam, for doing a great job. And that is again under the guidance of Dr. Modi sir, our coordinator, our guide, and our everything one can say. Ideally speaking, you should have only one peak, PL glow peak, which is also to be symmetrical and reproducible. But it is very difficult to get such a peak. Glow core structure ideally single glow peak around, and that too the glow peak around 200 degrees centigrade is being prepared. most of the time people are publishing papers, presenting at various conferences, and they are advocating that we have obtained new TNG material, and this new TNG material is useful for radiation dosimetry. And then when we go for asking them what is the glow peak temperature, they say that 325. Somebody say that 150 and so on. This is not advisable. The criteria, which is very much clear, that the glow peak should be around 200. This 180 plus minus 20 degrees centigrade, that can be allowed, but not plus minus 200 degrees centigrade. It should have high gamma ray sensitivity, negligible fading of the signal on storage for few months at 20%. No fading upon post-irradiation storage of the sample under normal conditions of temperature, humidity, light, etc. Emission spectrum falling in to the range of commonly available detectors around that is 459. And linear, it should have linear dose response. As dose increase, the PLP intensity should also be proportional. Complete absence of pyroluminescence and mechanical damage. Easy method of preparation, which will lead to batch homogeneity. So method should be selected so that the if the product is developed in different batches, there should be homogeneity batches. Properties such as toughness and non-toxic, etc., which will facilitate handling. Reusability after the readout. Simple annealing procedure for reuse, because this is a thermoluminescence TLE material. After irradiation, once the gleams are taken, then the sample is to be annealed at suitable temperature, so that whatever residual radiations are there, we should get eliminated. So intensive thermal treatment is not advisable, and therefore simple annealing procedure is to be there for the product for insensitive to thermals. Means the product should be insensitive for its thermals, deformation, chemical stability, and interface with the extreme climate variations. Effective Z means atomic Z effective value close to the tissue 25% molecule. The other applications, which also leads to